So, hello everyone, welcome to the next lecture of the chemical dynamics. So, in today's class, we will study about the one of the different topic of catalysis, that is your acid base catalysis. Acid base catalysis. And in the acid base catalysis, what is acid base catalysis? In one of the classes of our chemical dynamics, we have studied what is catalysis. Catalysis is any process which actually where we have adding some foreign substance to a chemical reaction, and that foreign substances actually the amount of that foreign substances does not change before and after the reaction, but obviously that foreign substance alters the rate of the reaction. And here also we will alter the rate of the reaction by the addition of some acid and base from the external source, and we will add to the chemical reaction which is already going on. So we will see, after the addition of acid, some amount of acid or some amount of base to a chemical reaction, what will happen. If the rate of reaction increase with the addition of the acid and the amount of the acid before and after the reaction will remain same, then we will simply say the reaction is acid catalyzed reaction. And if we will add some base to a particular reaction, if the rate of the reaction will increase and the amount of the base before and after the reaction will remain same, then the reaction will said to be base catalyzed reaction. That means acid base catalysis, acid base catalysis reactions includes the reactions in solution include the reactions in solutions which are catalyzed by acids or bases or both. Okay, so if a reaction which is catalyzed by H plus or H3O plus hydronium ions, but not by Bronsted, not by other Bronsted acids, and Bronsted acids are nothing but the proton donors. Is said to be specifically proton catalyzed reaction. Proton catalyzed reaction. That is, which is catalyzed by H plus amount. Reaction which is catalyzed by H plus will said to be a specific, that means it is a specific to H plus only or the proton, therefore it is called as specific catalyzed reaction. Okay. Similarly, if a reaction is catalyzed by Bronsted acid, will be called as general acid catalysis. General acid catalysis. If by proton, then it is called a specific proton catalysis. If by Bronsted acid, it will be called as general acid catalysis. Similarly, if a reaction is catalyzed only by OH minus ion, hydroxide ion, then it will be said to be a specific base catalysis. Specific base catalysis. OH minus, it will be said to be a specific base catalysis. Similarly, if a reaction is catalyzed by Bronsted base, then it will said to be as general base catalysis reaction. General base catalysis reaction. So at first we will study about the acid base catalysis. Acid catalysis reaction. So I will start this topic with an example. So let us consider one of the example. First is your ketoenol tautomerism. So what will happen? Let us say this is a keto group is there. Okay. You have added some of the base to it. What will happen? It is a lone pair. There is electron density. It will attract the proton towards itself, and due to which there is a creation of positive charge density over the oxygen atom. As a result, on the oxygen atom, the positive charge density cannot remain. Why? Because oxygen is electronegative in nature. It need to neutralize this. So what will happen? The electron density from the carbon-oxygen bond will be shifted towards oxygen, and due to which this carbon-carbon bond become weaker, and due to which this carbon-hydrogen bond become weaker, and due to which this hydrogen can be removed as a H plus, and this bond will be shifted as a carbon-carbon pi bond will be formed, and this pi bond will be broken down and shifted towards oxygen atom, and you will see H plus is removed out, and you will form OH double bond CH2. That means ene is there, ol is there. Therefore, this is the enol form. And in every step, equilibrium will be maintained. Okay, this is the keto form. Okay, that means here proton is absorbed by a substrate molecule, that is a ketone molecule. Then another proton is released. That means what is happening? Whatever the amount of the proton will be received here in this first case, that amount of proton is released in the final step. So due to which what will happen? The amount of H plus before and after the reaction remains same. Henceforth, what is happening? H plus is actually first chain of the ketoenol tautomerism. Therefore, H plus, the amount of the H plus does not remain same before and after the reaction, and also it is accelerating the rate of the reaction. Therefore, you can say H plus is acting as a catalyst. Okay, similar type of examples are there, like hydrolysis of ester. What will happen? Let us take a ester. Okay, let us add some H plus to it, to the solution containing ester. So what will happen? There is a larger electron density over oxygen atom. It will attract the H plus ion and the ester will be protonated. The ester will be protonated. Now what will happen? Obviously the solution will be taken in a solvent medium, and their solvent may be water. So over the oxygen atom, this positive charge is not stable for a longer period of time. So what will happen? From the solvent, there is chances that this water molecule can attack the carbonyl carbon. As now carbon is become much more electrophilic in nature, and due to which what will happen? Slowly carbon and oxygen bond will be formed, and what will happen? This oxygen can have the tendency to attract this H plus. So as a result, what will happen? There is simultaneously breakage of carbon oxygen pi bond here. Shifting of electron density leads to the neutralization of the charge on the oxygen atom, and simultaneously the transfer of proton from the water molecule to the OR group can take place. So a situation can arise like this. Okay. So what can happen again? Now what is happening? The carbon, the sp2 hybridized carbon is now converted to sp3 hybridized carbon. Okay, and what will happen? But now this carbon want to gain its sp2 hybridized character. So what will happen? Again this bond can be broken down, as this is more polar in nature, this polarization, and due to the shifting of this bond, this carbon oxygen bond can be broken down due to the polarization, and there is formation of RC double bond O OH molecule along with the formation of ROH molecule along with the formation of H plus. That means what has happened? The H plus which is gained by the molecule, is re-released in the solvent medium. Therefore, what you can say, the amount of H plus does not change before and after the reaction, and also the addition of H plus actually makes the carbon much more electrophilic, which results in the faster attack of the water molecule to the carbonyl carbon, and therefore actually the addition of H plus to the ester makes this hydrolysis process much more faster. Therefore it accelerates the rate of the reaction. Therefore you can say H plus accelerates rate of ester hydrolysis, and therefore what you can say, H plus acts as a catalyst here. Okay, so we will try to, this is the possible mechanism, but we will try to understand the kinetics of this acid catalyzed reactions. So let us start the kinetics of acid catalyzed reactions. Kinetics of acid catalyzed reaction. Kinetics of acid catalyzed reaction. So there are two steps. In acid catalyzed reaction. Also, the acid catalyzed reaction can follow two mechanisms depending upon which substance is actually receiving the H plus in the final state. So in the first mechanism, we will consider if a solvent is there and that solvent is water, and if that water molecule is receiving the H plus in the final step, then this is the first mechanism which we are going to discuss. So in the first step, the substrate molecule will be there, which can be ester, can be keto form, and that is receiving H plus from the acid. Now obviously there will be equilibrium, and what will happen? The substrate will receive the proton, and the protonated substrate will be formed, and there will be release of the anion, or this is the conjugate base. If it is acid and A minus, acid and A minus, Ha and A minus are the conjugate acid base pair. You have well known in the Bronsted concept. Next, in the step number 2, what will happen? This protonated substrate will lose the proton. If water molecule is there, that will accept the H plus from the substrate and leads to the transformation of substrate to a product species, which we have just seen. In case of your ester, it is converted to acid and alcohol. In case of your keto, after the removal of H plus, it get converted to enol form. That is the final product which I am talking about. And obviously the H plus will be released and it will be forming H3O plus. Okay. So in the first step, substrate absorbs or get protonated and form protonated substrate complex. Okay. In the second step, the protonated substrate complex releases proton and the substrate gets transformed to product. This is second step. And if the rate constant for first step is K1, this the backward reaction is K minus 1, and the second step rate constant is K2. So you should remember this SH plus is very higher energetic species. It is not a stable species which we have seen in the reaction. This is a very higher energetic species. It do have a charge on it, and generally the charged species are very high, have higher potential energy. Okay, and this is just like a transition state. So if you want to understand this, let us take another keto-enol tautomerism reaction. Okay, so H plus is there, so this will take the H plus ion. So what will form? There is a simultaneous formation of bond between O and H. Here del negative, here del positive, here del negative will be there. And if I draw a linear structure, and here this bond will be shifted towards this, that means this will be del positive, this will be del negative in nature. Okay, and this will be your transition state which I wanted to say, and this will be higher in energy. and this is your protonated solvent SH plus, which I am talking about in the kinetics. Therefore, SH plus is higher energetic species. Energetic species can be considered as transient species. Therefore, what we can apply? We can apply SSA, steady state approximation. Applying SSA to SH plus, we get. So what is SSA? So according to SSA, if any transient species is formed, that transient species, the concentration of transient species remains constant for a particular period of time, that during a course of a reaction. That means the change in concentration of transient species with respect to time will remain constant. That means it will be zero for a appreciable period of time. Okay, so in which step? That means this can only happen if the rate of formation of SH plus is equal to the rate of deformation of SH plus. So in which step the SH plus is formed? In the first step only. In the first step only it is formed. That means this will be, the rate will be equal to the rate constant multiplied by the reactant concentration, that is your S and HA concentration. Rate of deformation. In which step the SH plus is degraded, concentration is degraded in this step? Backward reaction. And involved rate constant is K minus 1, reactant is SH plus and A minus. This I am talking about, conjugate base. Okay, and also in the second step, SH plus, concentration of SH plus is degrading. But you should remember that here water is taken as a solvent. So therefore it will be taken is obviously in excess amount, and therefore very small amount of water will be participating during the course of the reaction, and that means which we can consider in practical sense the concentration of water will not change with respect to time appreciably. Therefore we can consider the concentration of water to be a constant. Therefore I will not involve the, while writing the rate of the reaction, and I will not involve the water concentration of water. So in the second step it will be K2 into SH plus. Okay, so K1 into S concentration into concentration of HA. Concentration of HA can be taken as a constant, a common, and K minus 1 A minus plus of K2. That means concentration of SH plus is equal to K1 into S concentration into concentration of HA divided by K2 plus K minus 1 concentration of A minus. This is equation number 1. Again, if we talk about the rate of the reaction, then obviously this rate of the reaction will be very fast in nature. Second reaction will be generally slow. That means the slowest reaction will be the rate determining step. That means second step will be rate determining step. Therefore, the rate of the reaction or the rate of formation of product with respect to time, the, or the rate of decomposition of substrate with respect to time will be equal to the rate constant of second step multiplied by the SH plus concentration. But SH plus is very higher energetic species whose concentration cannot be calculated or cannot be monitored with due course of reaction. Therefore, the concentration of SH plus is written in such a manner that, or in such a manner that we can consider or we can calculate the amount. Therefore, equation 1 can be used here, and substituting the equation 1 instead of SH plus, we can get S concentration into HA concentration divided by K2 plus K minus 1 into A minus. This is your equation number 2. Okay. So there are some special cases or limiting cases which we need to discuss. Bit number 1. If K minus A is very less than K2. So what will happen? In the denominator, K minus 1A can be ignored in equation 1. Therefore, what we can see, the rate will be equal to K2 K1 into concentration of S into concentration of HA divided by K2. Therefore, K2 cancel out. Ultimately, the rate of reaction is coming out to be K1 into S concentration into HA concentration. This is your equation number 3. That is, your rate is proportional to the concentration of substrate, and also it is proportional to the concentration of acid which we are adding. That means it can be considered as a general acid catalysis reaction. As the rate of the reaction is first order with respect to HA. Therefore, it is a general acid catalysis reaction. That is, rate depends on the concentration of HA. Here we are not considering only proton, we are considering the source of the proton, that is your HA. Therefore, it is called as general acid catalysis reaction. In the second limiting case, what can happen? We have considered K2 greater than K minus 1A. So, if K minus 1A minus is very much greater than K2, So obviously rate, that means we can ignore K2 in front of K minus 1 A minus concentration in denominator. Therefore the rate will be equal to, what was the rate expression? K1 K2 into substrate concentration into HA divided by what we have ignored, K2 we have ignored, so there will be K minus 1 into A concentration. But unfortunately from this expression we are not able to know anything. Therefore we will introduce some factors here. So what are the factors? If HA is a weak acid, obviously it will dissociate to H plus and A minus. Okay, H plus and N minus. So there will be a dissociation constant, and which is nothing but the product of concentration of H plus into A minus by concentration of HA. Here water will be there, but the concentration of water is taken to be constant. Therefore I have considered involve the concentration of water which is constant in Ka only. Okay. Therefore what is the concentration of H plus will be? This will be equal to HA by Ka is equal to concentration of HA by concentration of A minus. Okay. So this is your equation number 4, and that we will use. Equation number 4, if we are saying this, then this will be equation number 5. Okay. So now what we will do, we'll put this value of equation 5 in equation number 4. So what would be the rate of the reaction would be? The rate of the reaction would be K1 K2 by K minus 1 into concentration of substrate multiplied by HA by A minus is nothing but concentration of H plus by Ka. Okay. So this is a constant, this is a constant, this is a constant, this is again a constant. So we can write this is a combined constant, that is equal to K dash multiplied by substrate concentration into H plus. So rate, we got a expression for the rate, and this is your equation number 6, where the rate is directly proportional to the concentration of H plus only, specifically proton only, and this is first order. Therefore we can say the rate, this is called as specific proton catalyzed reaction, because the reaction rate is directly proportional to the concentration of H plus ion or the proton. Okay, so here what is K? Okay, so this equation 6th, we can write the equation 6th in different type. Let us say your rate is equal to K dash into H plus concentration into substrate concentration. So let us consider another K double dash into substrate concentration. That means your rate is directly proportional to the initial concentration, proportional to the concentration of the substrate molecule. So what is K double dash? K double dash is a constant, and this is equivalent to K single dash into H plus. And why it is a constant? Because K single dash is a constant, you already know. But you already know the amount of the H plus before and after the reaction remains same. That means ultimately the concentration of H plus is a constant. Therefore this is a constant, this is a constant. I will get another constant, that is K double dash. Okay. So what I can write here, let us say this, okay, let us multiply it by log in the both side. So log of K double dash is equal to log of K dash into H plus ion concentration, multiply, and this is equal to log A into B, log A plus log B. Okay, this is log K double dash. So what will happen? See what I am doing, I am just multiplying minus 2 times, and that will not remain, that will not change anything. Okay, minus into minus plus only, but this term will become pH, because pH is negative logarithm of H plus ion concentration. Therefore the equation become log K double dash into log K dash, minus will be there of pH. And therefore a new equation can arise, and this is your equation number 7. Okay, so now you can say that if a plot is made, if a plot is made between log of K double dash and pH, it would yield a straight line. And what is the slope would be? Line of slope minus 1. Understand? This is in y-axis, this is taken in x-axis, and whatever that will be multiplied by x-axis, that we will get m, or slope of the line, and that is nothing but the minus 1, and that is your intercept, y-intercept. So log of K double dash versus pH, there will be y-intercept, intercept is positive, therefore you can say this to be log K dash. Straight line will be observed, but whether the decreasing slope or increasing slope, slope is minus 1, that means decreasing, therefore the slope is equal to minus 1. Okay, so this is all about acid catalysis reaction, and this is all about. And similarly, if we use in the given step, where is the given step? Yeah, in the given step, if we will use base, then it will be simple base catalyzed reaction. Okay, but it is the first mechanism which we have discussed for the acid catalyzed reaction, which where we have considered that the water that is a solvent molecule is acting as a receiver for the proton, which is receiving the proton from the substrate proton complex. But in the other case, what can happen? In the other case, the anion formed or the conjugate base formed due to the dissociation of the acid, that will only receive the proton from the substrate molecule, substrate proton complex. Okay. If the conjugate base formed due to the dissociation of the HA, that conjugate base will receive the proton from the substrate proton complex, then there will be different mechanism. But the similar kinetics can be observed here, and that you can do at your home. So thank you so much for this class. We have completed acid base catalysis. We have tried to understand what is acid base catalysis, and we have tried to understand what is acid catalysis, specific acid catalysis, and general acid catalysis, and some of the examples of acid catalyzed reactions. And in the similar way, if instead of acid base is used, that will be base catalyzed reactions, similar kinetics can be observed. And if it will be directly proportional to the concentration of hydroxide ion, that will be said to be a specific base catalysis reaction. And if that will be depending upon the conjugate base, then that will be said to be as the general base catalysis reaction. And the similar kinetics can be achieved in that particular case. Okay. So in this class, this much only. Will come back to next class. Thank you so much.